Assalamualaikum warahmatullahi wabarakatuh and good morning. I'm Dr. Sababau from the Physics Section Pusat Pengajian Pendidikan Jarak Jauh, University Science Malaysia. This is course JIF 318 Quantum Mechanics. We are in Chapter 2 Complex Numbers and Linear Operators. This segment, Unit 2.4, will be on operators, its definition. Hopefully, after this lesson, you will be able to define what is an operator. Also, we hope that you'll be able to prove whether an operator is linear or not. An operator is different from a function. A function basically a fixed rule for taking a number and changing it into another number. For example, if you have a function y equal to mx plus c, you put in a value for x and you will get a value for y. That means the function basically take in a number and give you another number. While an operator is a rule for changing one function into another function. That means we are talking about changing a function. If you give in or take in a function, then the operator will change that function into another function. This is an example the differences between a function and operator. For example, on the left here, if you are given a function equal to x cubed, then if you put in a number, the function will give you a number. For example, if x is equal to 1, then the function is equal to 1, depending on the relationship of the function. If x equal to 2, then the function will give you a number 8. If x equal to 3, then the function will give you a number 27. That is the number in, number out. For a function, you give a number, then the function will give you another number. For an operator, for example, like an operator D here, an operator is recognized by a head at the top of it. Even though x, y, z might also wear a head as unit vectors for x-axis, y-axis, and z-axis, or sometimes people use I, j, k with heads on them to indicate unit vectors. An operator also, we use this symbol to represent D as an operator. Let's say D, an operator D here, in terms of G, and G is a function of X. Basically, this is equal to dg per dx. If this is the rule of the operator, that means operator D for gx is equal to dg per dx. Okay, so if gx equal to x squared, you put inside the square bracket here, then x squared, basically the operation will be dg per dx. So when you differentiate x squared, what you get is 2x. That means we put in a function which is x squared, and the operator gives you another function which is 2x, depending on the definition. This is just an example, okay? If an operator for sine x using this rule or this expression, that means d sine x per dx. That means you differentiate sine x, then you have cos x. So basically a function in, a function out. If you put in natural logarithm x or ln x, Then if you differentiate this, it will give you another function, 1 over x. So basically an operator is an expression where you put in a function, then the operator will give you another function. So those are the differences between a function and an operator. Okay. Usually in quantum mechanics, we need the operator to be linear. Okay. Especially in boundary condition and so on and so forth. So we need, most of the time we need an operator to be linear. So the condition for an operator to be linear are two. Okay, the first one, for every pair of function fx and gx, it means function of f and g. So L with a head here is basically linear operator. An operator can be represented by any alphabet. Here, since we are talking about linear operator, we use capital L with a head, and inside the square bracket here, we have fx plus gx. That means f function f and function g. There are two functions. This addition must be equal to the separate relationship. Okay, that means if you have an operator, linear operator, the summation of two functions will give you individual relationship between the operator and the function. That means L for f plus g equal to LF plus LG. This is the first condition. The second condition, for every function f and a real or complex number c, c can be real number or complex number. Remember about complex numbers that it has a real part and also an imaginary part. Okay. For every function f and real or complex number c, so we have this relationship, linear operator in the square bracket cf equal to c linear operator f. That means the c can be brought out of the operation here. Okay. Okay. So in other words, c is just like what you call it. Yes, it is just a number, real or complex number. So it does not get involved in the operation of an operator. Operator usually can be integration, it can be differentiation. That means some mathematical operation there. So C, since C is a number, it can be a real or complex number. So C can be brought out of the operation. Just like in integration, for example, if you have a number there, you can bring out of the integration, for example. Okay, so these are the two conditions for an operator to be a linear operator. Okay, so these two are basically the rule for a linear operator. This is an example question. Is an operator A for gx equal to gx squared linear? The x here as a function only. That means g as a function of x. So you can say is operator AG equal to g squared linear, something like that. Okay. For the answer, for the first property, remember that for the first property, the operator of a summation of the function equal to the summation of individual or summation of individual operator function. This is the first condition. Okay, so we try to look at this. That means if we want to prove whether an operator is linear or not, so it must fulfill these two conditions. Okay, let us look at the first property. Okay, we have the operator in the square bracket is the summation f and g. That means two function, and the relationship here that it is equal to the square of the function. So we have the summation of function. You square it. So what we have is f squared plus g squared plus 2 fg. So this is just multiplication by stages. That means you have f plus x multiplied by f plus x. Okay, so we get this. Okay, but if you just refer to the right side, okay, of the first property, we are still talking about the first property. The summation of two operators or individual operators for f plus g should be equal to the operator for the summation of the two functions. But now, if you look at the right hand side, af plus ag, for in each operator, it follows this rule. Okay, so the operator f will give you f squared, and operator g will give you g squared. So for the right hand side of the first property, we have f squared plus g squared, while the left hand side will give you f plus squared plus g squared plus 2fg. So that means the left hand side is not equal to the right hand side. So this proves that this operator relationship is not linear because it does not fulfill the first requirement or the first property of linear operators requirement. So hence left hand side is not equal to right hand side. So you can conclude that operator A is not a linear operator. Let us look at another example. Is an operator G equal to dg per dx linear? So this is the operator abstraction or rule. Operator G equal to dg per dx. Let us look at the first property where the summation, the operator of summation of two functions equal to the summation of the operator of the individual function. So the first property on the left hand side is df plus g. That means your operator for the summation of f plus g, and the operator is defined. dg operator of g is defined as dg per dx. So you can substitute the operator with d per dx. Okay, and actually this is differentiation. And for the summation of f plus g, it can be separated into two, df per dx plus dg per dx. And df per dx is actually an operator of f, and dg per dx is an operator for function g. Okay, so you can see that this does fulfill the first property of a linear operator. Then we check for the second property. The second property, if we do an operation on c multiplied by the function f, c can be a real number or a complex number, and we replace the operator with d per dx as defined in the rule here. Okay, that means you differentiate c f. C multiplied by function f. C is a number, so c can be brought out of the differentiation. That means not brought out, eliminate, but you don't need to differentiate c. So you have c df per dx, but df per dx is an operator for f. So we have operator for c multiplied by function f is equal to c multiplied by an operator of the function f. So this fulfills the second property of linear operator. So basically, in this example, an operator with this rule shown above, an operator of g equal to dg per dx is linear. So the derivative operator is linear. So here you can see that how we can prove an operator is linear. The operator should fulfill the two properties of linear operator. We try the first property, then we try out the second property and see whether the operator fulfill the requirement as a linear operator. As a conclusion, an operator is a rule to change a function into another function. A linear operator is the most common requirement for quantum mechanics operations. We'll see later that operators plays a central role in Schrödinger equation, which form the basis for quantum mechanics. Thank you very much for your attention.